between multiple modeling types. I prepared this material for a different group originally, and it may be that the interests here are distinct enough that there'll be different questions brought to the fore. But I sort of delineated. So I've talked a lot and have lots of additional materials on sort of issues of trade-offs and differences between multiple modeling types. It's also an area we've published on quite a bit, as well as hybrid models. One of the things I'd highlight is that a lot of the uses of system dynamics traditionally, particularly within the health context, have been applying it to more at an aggregate level. In other words, where we're counting the number of people in the population in different states, as we indicated. So again, in system dynamics, you divide the population up according to their state or their properties, and you count the number of people in a particular category or particular set of states and properties. So this might be males under tuberculosis treatment, and males with tuberculosis that has not yet been discovered to bring them to treatment, and we count the number of individuals in that category. So this is very, very traditionally these sort of compartmental models used at an aggregate level to characterize infection spread or to characterize progression of things such as heart disease or diabetes or stroke, etc. And there's many, many models out there where you find system dynamics being used at an aggregate level. It's not its only use, as I emphasized. It can be used, for example, within an individual to characterize individual dynamics. But a fair number of those uses are even aggregate in character in the sense that they aggregate the immune system. So generally, it's a sort of more aggregate approach when compared with an agent-based model where the focus is really on delineating particular entities or agents at an individual level. And as such, I had sort of prepared some slides in this other case of sort of comparing individual-based and aggregate-based modeling. As I see that as sort of the most salient, sort of salient difference that one is often grappling with. To what degree do I really characterize things at an individual level? Put in an extra effort to kind of represent things at an individual level. To what degree are aggregate representations suitable for my needs? I have some additional comments here on discrete event modeling and sort of clues that might hint as to when that seems most appropriate. So people will often ask me, because I use all three approaches, people, as well as some others, people also inquire with me, when should I use one or the other? These are some sort of heuristics that I put together, common motivations which might point you to the need to represent things, the desire to represent things at an aggregate level. One reason that a lot of people use is they want to run their model very, very quickly for some reason. For example, maybe you want to use your model as part of Markov chain Monte Carlo techniques, and you get it to run hundreds of thousands of times in the course of an hour or two or something like that. Maybe you want it to be responsive to user interactions. You want stakeholders to be interacting with your model in a very fluid way, running scenarios and to see results immediately from those things. If you want your model to be whip quick in terms of executing, there's several ways to do that. One of the most obvious is to sort of make use of a model which has fewer moving parts, a more aggregate model. So that model we saw of SIR in implemented in an aggregate way is very, very rapid compared to that very first model we ran, which may be on the same size population. Aggregate models, ladies and gentlemen, are invariant in their speed as to the size of the population. If you double the population size, it has no adverse impact on the speed of the model. It's just larger numbers in those boxes. Instead of being 1,000 people in that box, it's 1,000,000 people. It doesn't impact how fast it computes the formula for how many people get recovered or what have you. It scales totally transparently with number of individuals. So if you have a large population you need to execute quickly, an aggregate model is something that has attraction from that perspective. If you're seeking to understand how your model will behave under a wide range of conditions, or all possible sort of values for parameters, so we're seeking to mathematically analyze it and determine the shapes of sort of possible trajectories of the model. We know how to do that with aggregate models. There's a whole subfield of applied math that we call dynamical systems theory, and we can analyze the equilibria value of this model, say what equilibriums it goes to, what are the stability of those equilibria, does it get attracted to this equilibrium, to this sort of rest point where everything's in balance, like a endemic equilibrium or like a disease-free equilibrium. So it's something where it's unstable. If a single person comes into the Saskatoon airport with Ebola, we may be in stasis with respect to Ebola right now, but it's an unstable equilibrium. You bring someone with Ebola to the airport, and all hell breaks loose, and we suddenly have an Ebola outbreak. That's an unstable equilibrium that we're in. If you're seeking to really mathematically understand what's going on, there's a whole edifice of applied math that can be used for aggregate models. And we've done a fair bit of that in my group, and it's sort of popular cottage industry and sort of the infectious mathematical epidemiology of infectious diseases. If you want to do that, really folks, you're dealing with aggregate model. People don't know how to do it for aggregate model. Maybe a generation hence or two will have the requisite tools. There's some sort of tentative forays as to what they might look like, but really if we want to describe behavior, what's all possible behaviors that can be produced through this model? Or what are the equilibrium, what's their stability, and under what conditions will they be stable? You're dealing in this area. I doubt that that's a strong interest to people here, but there is a group of people for whom that's a key interest. They don't want to just run the model for particular assumptions. They want to say, what are all possible sort of patterns that can come out of this model? Could I prove that this will never yield an outbreak under these conditions? If you want to do that, you're talking aggregate models. And there's a set of mathematical tools, tools like control theory, for example, that can be used to sort of manipulate response to something like an infectious disease outbreak, or even in principle to sort of help guide people as to the best way to manage high demand within a health services context, or even things like at a physiological level, manage blood glucose levels following meal ingestion in terms of administration of insulin. There's this whole area called control theory, which formulates a principled way of sort of behaving, implementing policies in the most optimal way to control the situation and maximize some sort of goals with respect to the situation. So there's a lot of math here, and I think there's at least a few people in the room who are kind of interested in this, so I mentioned it there. Really, if you want to operate with control theory, it's easier to do with aggregate models, although not impossible to do with others, but there's certain types of analysis you can do with aggregate models that will facilitate it. If you have a huge amount of historical data, and you need to calibrate your model simultaneously with respect to all these different types of historic data, and that may mean running the model under very different sorts of situations. It's certainly cheaper to do with an aggregate model, a lot cheaper. we'll see how calibration is done with an agent-based model, and NA-Logic provides admirably rich functionality for doing calibration, but it's slower, more expensive, and you have to deal with the fact that not only is it slower to run the model once, it's also slower because you need to run the model generally many times because there are stochastics involved. You don't want to be just dealing with the vagaries of one particular run you did, happen to be lucky and have a really good match, but other runs are very, very poor matches. So when you're calibrating, as we'll see, when you're trying to use emergent data you have on emergent behavior of a real system and trying to match model outputs based on that, which is a very valuable source of data you can't just put into the model as sort of parameters, but if you're trying to match those two, it's quicker to do with an aggregate model. On the other hand, the agent-based model, or model with stochastics, will capture some features of that data that may be very important to you, like variability in the data that you see, the noisy character of the data. You may be able to reproduce that at an individual level in a way you won't for an aggregate level. So there are some trade-offs there. Sometimes you're working with stakeholders who are much more comfortable thinking at an aggregate level and will kind of push you in that direction. Demographers are a sort of example group that tend to think, they're often going to be thinking at level of aggregates, sort of characterizing the population into age categories, into different groups. And sometimes an aggregate description is a very natural one for dealing with them. And I'm not saying that that's an overriding phenomenon, but factor, but it is something you want to become. When you're dealing with people for whom you're building this model, or key members of your team, it often is very useful to be able to work with a model that speaks to their understanding, that can leverage their data, and that can tell stories that they can relate to. Therefore, considering sort of stakeholder needs is pretty important. We'll see this again in an agent-based context, because some types of stakeholders, like doctors, clinicians, they deal with patients. They deal with particular people. And often you show them an aggregate model that depicts, people into a set of categories and the count of people in different categories, and they can't relate to it nearly as well as they can to an individual level depiction. If you have situations where you have subgroups in the population, but they're not so much behaviorally different in a qualitative fashion, but they differ in sort of degree, in sort of how frequently they mix with one another or what have you. You can often characterize this very well using an aggregate model by subscripting. In other words, by stratifying the model, say by mixing category, or by age group, where the age groups differ in their hazard rates of developing, diabetes or what have you. Subscripting is if we have an aggregate model. I'll get to you in just a sec. If we have an aggregate model, let's suppose something like this. In NA-Logic, in Benson, Carson, many other system dynamics packages, there's a way of conveniently stratifying this model according to other categories than what you see here. So let's imagine here, Dawood, that we want to simulate spread of TB in the population among different groups, okay? Maybe within our province here, we actually are a little bit unusual worldwide in the sense that we have many cases, most cases, half or more, are among children. There's many reasons for that. And kids have differences with respect to their likelihood of transmitting the infection. It seems they're likely of developing, of getting infected and presenting with active TB disease, going through what's called primary progression. So we might want to distinguish people by age categories here. Another distinction might be by ethnicity. So we're in a situation here where the south of the province, for example, has a TB situation more similar to what you see in many developed countries. Our north and predominantly Aboriginal population is afflicted at much, much higher rates, like 10 times to 20 times higher rates of TB. And so we might want to distinguish this model by ethnicity. Among other things, we have tons of data that's broken down by ethnicity. We might want to make sure the model captures that well. So imagine that we want to divide up this model to keep track of people, not only by stage of progression of TB, but also by their age and by their ethnicity. Okay? Conceptually, what's going to go on is that we'll have an uninfected category for children, for First Nations people and children who are perhaps from immigrant populations, and children who are the balance of the population. Similarly, we might have latent for each of those combinations, and then adults. So you have sort of all combinations of age on the one hand and ethnicity for each of these categories, right? So when you do that, you could copy this model and paste it. So you have TB under treatment for children, First Nations, TB under treatment for children, immigrant children, TB under treatment for children, other, and then you'd have tuberculosis without treatment for each of those categories as well. But it gets really tedious to do that, and that's error prone. You copy it, you have a problem, you need to fix it at many different places, and you forgot to fix some of the places. So it's awkward, it's tedious, and it's unnecessary. You could express the same model in a much more compact way with what's called subscript. And so therefore, it's kind of like you have, let's call this category T, okay? T. I could call it, I'm going to subscript it by age by making it T sub A, and then further I'm going to subscript by ethnicity, T sub A and E. Or more commonly, as we write it, T sub A, E, right? And what that means is there's actually, this one variable actually represents, maybe 6 different variables just by subscripting. And system dynamic packages, and any logic certainly being among them, allow you to very compactly do that. And that's your primary way. I mention this because that's your primary way of representing heterogeneity within an aggregate model. Don't be fooled into thinking you can't represent heterogeneity in an aggregate model. You can. You divide it up according to the categories of people. So according to their states or according to their properties. In this case, it's sort of states and properties. Age is kind of a state that changes over time. Ethnicity is a property of that person, an attribute of the person that doesn't change over time. So in an aggregate model, you divide up according to those categories. In an agent-based model, you divide up according to people, each maintaining their own state. Here, you divide according to categories of state, and you count them with people who fall in that category. So this is subscripted, and that's the way that we would keep track of heterogeneity within a model like this. Does that make sense? Okay. There's theoretic consequences for that. A model like this scales really well with population. Double the population makes no difference. 10 times population, no difference. 100 times, no difference. What does make a big difference here is you add heterogeneity. Let's suppose we want to distinguish between men and women, for example. Within this model, we would have to double the model size. Now suddenly you go from AE to T sub SAE. It doubles the model size in terms of the number of compartments that you have. And in general, it's awkward. You have to do global work across the entire model to add that extra distinction according to heterogeneity. How do you add heterogeneity in an agent-based model? Let's suppose we wanted to have persons, but broken down by sex. You add a parameter. Do you have to go modify things at all places in the model? No. No, you do it basically at one place. You can use it at many places, but within an aggregate model, you actually have to go typically across all stocks for the population, change all of them, all the flows between them. You have to update all of them so it carries that information with it. It's a lot of work. It's a lot of work. So flexibility with respect to heterogeneity. If you're not sure what details you want to put in the model, what types of distinctions you want to capture, it's actually much easier to do it in an agent-based model than it is in an aggregate model, because it just, the amount of work required to change that is vastly less within an agent-based model. Does that make sense? Okay. So, aggregate model. Another thing is, if you have no recourse to people who know anything about Java, if you're all alone and you're not interested or inclined to invest in trying to learn at least a plausible beginning amounts about Java, going out and buying, Java for Dummies or what have you. If you're not willing to sort of, you don't have the time to invest in picking up a textbook in it, and you don't have anyone you could call on, you're going to want to think carefully, about whether you're going to be able to deal with writing those little bits of code you're going to need. You really want someone to call on. We're trying to simplify this. We want to provide an easy pipeline in case you people want to have continued contact with TAs here and so on. Kurt's up for bid. But the fact is, you want someone you can draw on occasionally, just like you want that biostatistician you can draw on if you're an epidemiologist. You want that sort of person you could draw in when you're encountering some problems. So if you have absolutely no ability to do that, and you don't want to bid on Kurt or something like that, if you don't feel that you're in a position where you could take advantage of asking questions with those who do know something about Java, aggregate models are great. I mean, people routinely work with aggregate models and they do no programming in any conventional sense of the word. They put down forms. It requires crisp thinking. It requires being precise, but it doesn't require programming in any sort of sense. Now, personally, I think agent-based modeling is going in this direction, and I have a substantially long-standing research project sort of impetus in this area, and fortunately we're in discussion with the Logic folks about how they can learn from what we've learned about sort of ways of describing models. I think it is deeply unfortunate that you have to make use of a language like Java to do any logic type work. I think there's much better options available, and I think in the 5 to 10 year time frame, you may find doing agent-based modeling getting closer to the level of technical sophistication required to do system dynamics modeling, putting in formulas at artful places, and hopefully eventually being at the level where at a mechanical level, it's no more difficult than creating formulas in Excel or something like that. Conceptually, be more sophisticated, but to lower that need for programming per se. I speak as someone who has a computer languages background, and there's big advances there that can be leveraged that haven't been yet within the agent-based modeling area. So I think we're looking to help others. Question? Yes. Oh, I'm sorry. I've been neglectful, and I apologize. Yeah. Indeed. That's right. Yeah. That's right. But I think that's a lot of the need. So certainly the research question, I tried to articulate this early on in the boot camp. The research questions are the primary driver, but there are also sort of practical resource limitation questions which need to be factored in terms of do you have the requisite skill sets that you can bring to bear for this? Do you have the team members? Do you have the buy-in from stakeholders that also need to be considered? And sometimes we end up having a very clear research question that we would like to see addressed, but we don't have the resources, speaking broadly in terms of skill sets, in terms of people, in terms of data, in terms of understanding, to yet be able to get there. And so we end up making use of, say, a much simpler formulation than we would like, or a formulation that people in our team are comfortable with for the time being, to advance the discussion, to work towards that richer formulation. So, I think, a good example of that is actually sort of the chronic wasting disease project, which we saw yesterday, which really started in its earliest incarnations with an aggregate-based approach, and I was, unclear about how there were certain questions, certainly research questions, that seemed to point to an individual-based approach as one that could really yield some value, but we need to get started somewhere. And the people we had to work on at the time were much more comfortable operating at the aggregate level, and that helped really advance the understanding as to what some key factors were, highlight some things that an individual-based model could better shed light on and help motivate some of the individual-based models. So I think we're dealing here in a sort of practical milieu that requires us sometimes to prioritize our research questions and defer some that we're not yet ready to handle because we haven't yet assembled the understanding, people, the financial resources, the time, whatever it is, to sort of really take those on quite yet. Does that make sense? Yeah, and that's sort of the advice I had for, I think, your group and some of the other groups yesterday, is sort of try to articulate research questions, but identify which of them you might be able to make progress on sooner as well, because there's often a diversity of them, and there's things we really love to know, but maybe are too ambitious for now, and then there's things that we could act on sooner given the team that we have right here, right now, that sort of thing. Yeah. In sort of speaking to that, this issue that sometimes we have, sometimes we actually know a lot of things at the aggregate level that we don't know at the bottom level. One of the reasons that we engage in our data collection work with smartphones and measuring contact patterns and measuring people's physical activity level and mobility behavior, et cetera, using this IEPI tool that we've built, is precisely to inform gaps in our knowledge about what's really going on at the individual level. Traditional survey instruments sometimes are just not going to provide the data or more to the point, the understanding we need to inform an individual level articulation of what's going on, say for an agent-based model. Sometimes the understanding of what's going on there is just not there. Our theory, sort of how things work, is not yet there. Now that doesn't prevent modeling at all. There's certainly places where we'll model even in the absence of sureness of what's going on, but it may get in the way of addressing our research questions by building a model on which we have great quantitative confidence. So sometimes we have data at a higher level and and understanding only at a higher level, and we really need to sort of to leverage that to address those research questions which can be addressed by that. So there's a lot of work in areas of great interest to me that where the theory is still being put together about sort of the theory of human behavior, human choice with respect to that. And again, the issue is not mechanically creating a model which captures the theory. The question is the theory in place? Is the theory about how people behave in these situations, or, you know, the ways in which their decision making vis-a-vis eating behavior or physical activity are coupled in ways in which those depend on their social and physical, the built environment around them. Those pieces are just getting filled in now in the literature. And some of these tools that were mentioned earlier, when Jennifer asked about big data and sort of electronically sourced data, I'm convinced within the next 10 to 15 years, there's going to be an explosion of understanding at an individual level concerning individual behavior longitudinally, which you really would like to leverage with individual-based models. But right now, there are big gaps still, and that is to temper your ambition to sort of contribute at a quantitative level to discourse about these factors where there's gaps. Sometimes you're better off choosing your battles carefully, going up to an aggregate level where you do have some data, and confining the research questions you try to address to things you can more comfortably address at an aggregate level. So those are some comments there. So individual-based modeling. These are things that just smell to me when people describe their research questions. These things smell to me like things you really want to think seriously about maybe using an individual-based model. If you have interventions that depend on ancient history, or you have a whole lot of data that you want to match the model to on individual history, or biography as we might call it, that's a good motivation for individual-based modeling. Now suppose you want to simulate policies who distinguish between individuals based on their past encounters with the healthcare system, based upon their past treatment history or their past presentation history. Here, if we need to accumulate that sort of history information, you're not going to be able to do it effectively in an aggregate model. You're not going to be able to disaggregate it by ancient history typically enough to address this. Sometimes you want to, like our work with diabetes, we're very interested in life course issues and how early life exposures prenatally and in the early years of life shape later trajectories. And we have extensive information biographically, occurrence of diabetes cross-linked to information on people's birth weight, et cetera. And if we want to match our model sort of results with that sort of data, again, trying to capture birth weight within an aggregate context would require disaggregating the population by different birth weight categories, which is it's just a huge cost for very prosaic sort of need. Much more easily done in an agent-based context. We can capture life course effects more readily. If you want to capture progression of agents along multiple pathways, comorbidities. So it was asked earlier, comorbidities. So maybe you're interested in Hep C and an HIV co-infection and the consequences for progression. Trying to capture comorbidities in an aggregate level requires an explosion of the model that's often both obscures understanding and is sort of time-consuming and also really slows it down and awkward. And so, at an individual level, you can do this much more easily. And any logic, how would you capture comorbidities? I've said it before, but if we had an agent in any logic, in an agent-based model, and we want to capture progression with respect to HIV and progression with respect to Hep C, how might we do it? What would be sort of one thing that comes to mind at least? Yeah, two different state codes, one for one for the other. This may seem obvious, but it turns out you can't do that in an aggregate level. In an aggregate level, you have to consider all possible combinations. Okay, they could be in this HIV state and that Hep C state, or the same HIV state and this other Hep C state, or that same HIV state and this third Hep C state. You have to consider all possible combinations of them. And it just blows up in your face the more comorbidities you want to consider.
In defense of that,
yeah.
the aggregate
a good question. I mean, here in this province, we have very, very high rates of co-infection for HIV Hep C. I mean, I think it's, gosh, if I'm not mistaken, I think that, Cheryl, I don't know if I'm off on this, but I thought it was like majority of HIV cases are also infected with Hep C. I think from the Johnny Cattell Health Region, from Maurice Henry, I heard in their health region it was something like 80%, if I'm not mistaken, which is, you know, very, very high, and high enough that you know, if you wanted to represent the HIV situation in the province, if you left out Hep C, you'd be potentially missing something pretty important. Not least because it's also interactions with the contraindication for certain types of drugs because of liver impact and stuff like that. You're right. It's not in all cases, but for certain cases, you know, considering several comorbidities. If we want to have learning by agents, or we want agents to be able to capture memory, if we want to capture effects in our models to address our research question, if it's important to simulate how agents learn over time, or you know, have learned behavior, or remember something. Maybe it's as simple as remembering past occurrence of infection in a more articulated way. So they have, you know, some buildup of immune memory. So it may not even be more cognitive level factors as so much as physiologic, or other history dependence. This is a big motivation for agent-based model, or quite a substantial motivation for agent-based model. Trying to capture sort of learning by agents with an aggregate model, to have agents sort of change their behavior in substantive ways based on their past experience. It's hard to do really well at an aggregate level. There are some interesting literatures on firm learning and sort of learning curves by firms, but capturing this at an individual-based level is sort of easier. If you have agents and you want to capture localized perception among agents, an individual-based model can be very valuable. What do I mean by localized perception? What I mean is that an agent's behavior may depend on the particular subset of information that they see or they perceive in their current situated context. Give an example here. 50 years ago, a lot of the modeling that was, I think most of the modeling that was being done of traffic jams and sort of congestion was differential equation-based modeling. You use differential equations to kind of capture the flow of cars along the road. And people realized there were certain types of phenomena that weren't well captured because of that, or you know, in that framework. For example, cars slowing down before a road sort of rises, you know, over an overpass, for example. They would slow down because they don't know what's on the other side of the overpass, or they slow down before going around the curve. They'll tap their brakes when they're entering something where they can't see quite what's ahead of them. If you try to characterize these things with a differential equation format, it becomes quite awkward, especially if you want to think about things that will change that informational environment. For example, things that would straighten the road, or things that would provide information about whether there's free driving ahead or what have you, improve the visibility, and now, you know, what's the dominant trend now is towards individual-based modeling of individuals in cars. So Moshe Ben Kiva's work, for example, starting in the 90s, I think it was, of individual drivers in cars making decisions about which way they're going to go, simulating what they see and, you know, the response on their driving behavior for what they see, and how that propagates to other agents. So they tap on the brakes, someone behind them sees them tap on the brakes, they tap on the brakes too. You can capture those effects, that sort of localized perception. What do they see locally, and how is it affecting their behavior, and how is that translating to other people's perceptions? Doing this in an agent-based context is certainly far easier than doing it in an aggregate context. If you're trying to, by contrast, intervene in change behavior on or explain phenomena across a network. If you want to characterize sort of network dynamics, where to intervene in a network, which hubs, for example, you might try to influence, or hubs on which you might try to collect information. It's much more readily done at an individual-based model. You can characterize the networks, you can characterize the impact of network change, etc. If you have a lot of heterogeneity, it's much easier to do this within an individual-based model, especially if you're trying to sort of explore different heterogeneity, whether we should include this or not. If you want to capture the impact of the intervention across many categories, so you're focused on intervention, understanding an intervention, but not only the overall impact of the intervention, but transfer effects. Effects where this intervention preferentially helps this group at the expense of this other group. This is something which you can capture because of the ability to represent heterogeneity in the population. You can capture this more readily within an individual-based model. You can do it with stratification to some degree, for sure, but if you start having many categories, it becomes much more natural to do it within an individual-based model, because you can capture a richer representation of the heterogeneity and break it down flexibly by different groups as you see fit, rather than structuring the whole model to be broken down, say, by these age categories. You could have people broken down by whatever age categories you want in an individual-based model. Some of the example models I've provided to you, it's very easy in any logic to have agents have continuous age. You don't have to divide them up to age categories, 0 to 4, 5 to 9, 10 to 14. You can, sure, it's no problem, but it's very straightforward to have them have continuous age. And then you can summarize it in whatever age categories you want to match your data. This is something that's very readily done in individual-based model, not very readily done in aggregate model. Sometimes we just know things much better at an individual level, or it's easier to describe. Some types of stakeholders want to work with individual-based models. They just find it vastly easier to relate to, and they just tone out when you're dealing with higher level models. And finally, and this is a very, very important one, if you want to deal with behavior across multiple scales within, beneath the skin, social behavior, levels of context, school, neighborhood, city. If you want to deal with all those different scales within your model, what you have in individual-based models is a natural nesting of the model that mirrors the nesting in the world, mirrors sort of the levels of context. Within an aggregate model, these things can be represented, but they're often represented in sort of a horizontal way that mushes them all into the same basic sort of levels of the model, which is often confusing. Within an agent-based model or an individual-based model, a sort of more general category, you can capture those levels of context in a very natural way because they mirror the nesting you see in the world. So you could summarize data, for example. I don't know if anyone here does mixed effects models or models with hierarchical linear models that try to capture different levels of context. You can very easily generate those from an agent-based model very readily. You could summarize things at the neighborhood statistics at the individual level, neighborhood level, city level, in a way that trying to do that within an aggregate model is just going to be kind of a fool's errand. You're going to be a very big difficulty capturing that. What are some limitations of agent-based models? Well, some people, you can't really mathematically analyze. Our knowledge is not there how to mathematically analyze them well. So we really have to do things run by run. We can't say, okay, this model in general is going to have these equilibria at these locations as given by parameter in terms of parameter values. We can say maybe if we run this model out where this model stasis points tend to be, but trying to get those as a function of the parameters is you can do it in certain cases, but it's much more challenging. There's run times. You have to run the model many times, maybe 100 times to develop confidence that the trends you're seeing are reliable. 100 is a lot of times, and people often do it many fewer, but the point is the model takes longer to run, and you have to run it a number of times. And this can lead to a lack of interactivity and associated opportunity costs. It can mean that you don't get to run it interactively and get that kind of very quick feedback for your aha moments or your insights. At an individual-based model, you can calibrate it to all the data you want. You're probably not going to get an exact, unique sort of initial state for the model or unique interpretation for what exactly is going on at the micro level. There's just not enough data to tell you the exact state everyone begins in or something like that. There's typically a lack of data at that level. There's some software engineering or programming that's required in building the model and modifying it. Ladies and gentlemen, I know this looks painful for many of you, but I know I answered this job. If I could only show you what I've seen with packages from other frameworks. So right now I'm just gotten involved in this project. I won't, because this is all public. So it's on YouTube. I'll limit my comments. But it's a prominent project. Very powerful agent-based model looking at chronic disease related. I'll leave it there. And so with some absolutely top-notch people in the States, leaders in the field in the area of, in some cognate areas and in this area. So it's a wonderful team, fantastic resources. They've done years of work to kind of align the model with actual data and so on, and it's fantastic. Their model can capture all sorts of factors, explain certain patterns that otherwise people have thought you have to build directly into the models. They can explain the emergency patterns of philosophies. It's great stuff. So Dylan and I have both seen the code base for this model. So we went down there and looked at it. This is in a framework called Repast. How many people here have heard of Repast? Okay, so Repast is maybe the #1 agent-based modeling framework out there. It's a great framework. I've done a lot of work in Repast in my time. And there's a lot of richness there. It's very powerful. But ladies and gentlemen, in terms of the level of software engineering required to build a Repast project, it's at least an order of magnitude, maybe, I don't know about 2 orders of magnitude, but between 1 and 2 orders of magnitude above what you see with Honeywell. I mean, it's like night and day. So what I saw with this model is, dozens and dozens. I think it was between 50 and 75, something like that, Java files that are being maintained. These are Java files on all sorts of things. Java files to read parameters in, Java files to create graphs, to show certain output, Java files to output data to certain tables. I mean, you go looking at any logic model and you see the state charts, you see the events, you see, the stocks and flows, or you see the overall layout of what parameters are there. You want to see that in a model like this, you got to go and you read the Java code. And it's page after page after page of Java code, and a given one of those dozens of files. And it's not very well commented. It's structured in a way that works, but is not very flexible. And here you're seeing, premier leading projects in this area put at risk because of the vagaries of how much programming effort is required to maintain it. You're talking about something that is comparable to many software development commercial software development projects in terms of the level of effort being required to maintain this thing. And a lot of it is prosaic stuff that in any logic is built into the software, and you just, you say, okay, I have a graph, this graph depends on these things, and that may be pages of code within this model. And every time you want to go add a title to that graph, or you want to get it to display this other thing, you got to go modify that code. It is painful, but not only painful, it's risky. It's putting the whole project at risk because there can be bugs in the code. And after publication, you realize, oops, that graph we thought was of this, it was actually of this other thing. Or this quantity we thought was recalculated, actually that line was commented out to recalculate it, and it actually didn't recalculate it. It was just the initial value. And you got to issue an errata or what have you. So, they are, I wouldn't be exaggerating too much, but I said they're kind of drowning in this code. And really, it's a big software engineering It's like maintaining a commercial software project. And it has all the gravity of maintaining that well. So, if you don't have any recourse to people to be able to consult with on Java, you should be very careful about embarking aggressively in agent-based modeling. Give it a try, get your toes wet, and so on, and see how it goes. But see if you can develop those social networks with geeks like me. Well, okay, with people who have a diversity backgrounds in that area. But your folks are being spared the worst of it by use of any logic, by leaps and bounds. In agent-based modeling, though, achieving model transparency is harder. What's in your model? In case you haven't noticed, one of any logic's biggest weaknesses, and I hear this from person after person after person, myself first. I heard this from. You go to your any logic model, you open one of those models, and you look at it, and it's not clear where everything is. It's like some things are in person, some things are in main, but more to the point, some things in person are in the properties of the person, properties of person like the startup code here, other things will be in an event, other things will be in a transition. You kind of got to remember where are those things. I want to show you one trick that a lot of people don't realize with any logic. If you have one of your models up here, or maybe one of the models we built, or just one of the models we were looking at this morning, you go to one of those models, you go up and you look at, and I have to remember where this is exactly. I think it's under, it's under the tools. There's this thing, create documentation. So you select the model itself and you say create documentation, and it will tell, okay, where to put it, what file format should be in Word or PDF or something. And then it will go and it will generate the documentation for this model. This documentation is voluminous, but it contains basically all the things that you've modified in this model, all the properties of the model, and enough to produce the model from this, aside from external data which is read in by the model, etc. So here's, for example, a summary from this. So here we have main, and this is kind of the things in main, and there's a population called parameter size. Its default value is this. The environment has a continuous space, and the layout type, etc., is shown. And this basically gives you a depiction of all the things in the model. So if you are having trouble remembering where things are in the model, consider generating something like this and looking through it, because you may be able to quickly zero in on things that you had forgotten that you modified here or put in this other place. You can find it right here. AnyLogic is trying to clean this up a lot so that it will become much more transparent, easier to read, less boilerplate in it, etc. But already, this is just vastly better than not having anything. Just incomparably better. And it's literally one menu item that you do, and you make any options. So we can now put it in Word for you to analyze. So this is very important, but in terms of kind of transparency, in terms of sort of stating, what all the model assumptions are, achieving model transparency in an individual level model is somewhat hard. As much model transparency as a simple page of or half a page of equations for a classic compartmental model. We're working towards this. This is something our group is pushing on. It's something that AnyLogic is paying attention to, sort of best practices here, trying to learn from it. Yeah, I give them great credit for doing this, for investing and trying to work towards greater model transparency, because they know that this is a weakness, something they've got to work on. But I hope that thing from generating model documentation will be useful there. Traditionally, in the agent-based modeling area, there's been less attention to what the modeling process is. There's some good papers which lay out some basic approaches, but there's a lot more thinking which has to be done for sort of formalizing how to do agent-based modeling engagement with stakeholders better. How could we lay out the different stages of it, have a very well-defined validation process, etc. And finally, I think you saw this yesterday with Gregor's model. The need to represent individual level detail may require extra detail, dealing with details that are otherwise kind of nuisances. We don't want to have to deal with them, but we kind of got to, in order to create the model to address the level of interventions that we're thinking about. We want to think about certain awkward things. I'll give you a vignette he didn't give from yesterday's model, but it occurred very early on. So that model was created in the first version of that model was created in one of my classes here. And Cheryl was involved in helping to guide it. This is maybe 2 or 3 years ago now. And I met with the student team at a couple points through the semester. And towards the end, I had sort of urged them to think about seasonality, because seasonality, my idea was that animals cluster in the winter. I heard this from Cheryl, I think. They kind of cluster in the winter and sort of try to stay warm, and I thought that was interesting. And also they can't move as easily through the snow, so they're limited in their browse sites or what they can eat. So within this model, I kind of pushed them to consider seasonality. And the other thing I was really interested in is, so here in Saskatchewan, folks, Saskatchewan exhibits what might be called pronounced seasonality. And we have a thing here called winter. And you folks are largely innocent of that. But I'd invite you back for a winter boot camp sometime. And in the winter, there's things that happen that are unusual. For example, things freeze up. The river freezes up. Lakes freeze up. The inside of your nose freezes up sometimes. But that's another matter. Because of that, we have this phenomenon where deer can migrate across the river, across water bodies that are otherwise boundaries. So that Antelope Creek area borders on the South Saskatchewan River, they can run across the river at that time, which may mean mixing of deer populations that otherwise wouldn't be able to be mixed. In any case, I asked them to put in freezing up of lakes and rivers, and so they said, yeah, we'll do that. Great. So early on, and then the final version of the model was approached. I noticed that wasn't in there. So what's up? Why didn't you have freezing up of lakes or rivers in there? And they said, yeah, we did it initially. We put in so that the deer could run across. There was no problem. They said though there was a thing we hadn't thought about that just we didn't know how to fix, and so we eliminated and we got rid of the whole thing. We got rid of their ability to run across. I said, well, what would cause the problem? They said, well, okay, so freezing up was fine, but what happens when it thaws? And I said, well, what's the problem? And they said, well, what happens if there's a deer on the ice when it thaws? Like, where does that deer go? Does it swim then, or does it drown, or does it suddenly get teleported to the nearest place on the ground? And they said, we didn't know how to deal with this, and it was too awkward, and we just deep sixed the whole thing, and said, nothing's going to freeze up. And this is what I mean by sometimes these models require representation of extra detail, like weird cases that you don't really want to deal with, but you got to deal with it for it to be consistent at some level. I think I told them, well, just transport the deer like to the nearest shore or something like that. But the point was, it's awkward sometimes. You have to sometimes be dragged into little bits of detail. You think are needed to address your research questions to get the model to that point, but you're not absolutely certain. So these individual-based models are awkward in that way sometimes. And sometimes they push beyond available data sources into a bit of speculation about what's going on, and you got to bear that in mind, what the grouping is, etc. And it's a downside. On the other hand, they give great generality for looking at counterfactuals that you might not be able to reliably evaluate. You probably won't be able to reliably evaluate with an FPA. Okay, so those are some comments on aggregate, individual. Just make some comments on discrete event modeling. What sort of flavor of things might, if you smell it, might sort of make you gravitate towards the discrete event kitchen? Well, if someone's talking to you about a defined workflow involving several stages of processing, and where resources are required to process these things. The time needed to go through it depends a lot on, is a resource available? There's waiting times associated with it. It's not a continuous flow like of chemicals, but it's a flow of sort of individual discrete things, patients, cars, widgets, patient flow through facilities, or it's processing of vaccine doses to get them ready for administration to people or what have you. Starts to smell like discrete event modeling, particularly with the need for resources and waiting times and queues. That will be often a dominant feature. If you're interested in understanding how movement within an irregular facility, for example, might be slowing things down, you're interested in how placing resources within that facility might speed things up or allow for greater efficiency. These are things you can readily do with discrete event modeling, whereas trying to do it in an agent-based way, you could probably force fit it, but it would be kind of overkill, and you'd end up reinventing a lot of stuff you don't need to. The good news is agent-based modeling and discrete event modeling sort of coming together in any logic 7 in a big way, and so you're going to be able to have very flexible sort of interactions between these things. If the primary ways in which the things that are flowing through here interact are queues and resource availability, this is kind of a good thing. Imagine you have a situation where patients present for vaccination and you're really concerned about infection of people while they're waiting in line based on where they're located within a facility. Trying to do that right now in any logic 6 with discrete event modeling, I think it might not be, certainly without agents being explicitly represented at some level, I don't think you're going to be able to ask the discrete event modeling framework, where is someone located physically right now, how close are they to another entity. Is that correct? Can you in discrete event modeling right now ask where is this entity located in space, how close are they to another entity?
You can if you have it.
Sure,
but
exactly. I said, without agents.
Without that is meaningless.
Exactly. So, and so it's really in conjunction with agents, and the good thing is that the entities and the agents are being merged together as concepts within any logic 7, so you can be able to do this really easily. But right now, a hallmark of discrete event modeling in its pure form is if the ways in which those things flowing through the system interact with each other is kind of through forcing each other to wait, because one has occupied the procedure room, the other has to wait for it. That's a sign of discrete event modeling is good. Or if there's a need for regular movement on defined paths within a facility, all those paths you saw people coming into the trauma center and circulating around, it's very easy to capture in any logic discrete event framework. They could be captured in agent-based modeling, but you'd have to end up kind of reinventing some of the wheels from that, et cetera. It would take sort of reproducing some of that functionality. So these are some things for discrete event modeling. I'm not doing this as much justice as I did the other two, but these are some things that to me bring to mind, maybe you're talking about a discrete event model being used for this stuff. So those are some comments on some of the trade-offs between these methods. In a separate session, I want to show you some hybrid models, and I know Scott has a really nifty one that links together all three of the components that you'd like to show. Any questions on this before we break for lunch? As groups, so like the patients coming in and then. Okay.
I mean, it's not a
Right.
biological question, but having I think we need to is that easily done, or is that?
Currently, the answer is yes, but you'd have to use the pedestrian library, not the discrete event library. Pedestrian library is used mainly for pedestrian dynamics, and it is used very, very specifically to model congestion and realistic flow of people. And something that the pedestrian library does right now, which will do a lot better than what 7, is that you can have a group who one, because you're using 681.
That's
I
right.
think.
That's correct.
681 doesn't have the heat map in it.
Oh,
The heat
Indeed.
map is going to really, I think, show some